哎，华明，
哎，杨艳你好。
你好，等一下子，
嗯，
等几分钟。哎，路易斯，
Hello, guys. And Juanmin, I haven't seen you in a while. I'll talk to you in a while.
Hey, Luis. That's because you did not go to KubeCon anymore.
I know. I need to, but the budget hasn't been there.
Well, it's a good investment, let us say.
Yeah.
Convince your company, promote the
Thanks.
visibilities, and send Luis to KubeCon.
Yeah, I missed it a lot. Yeah.
yeah, a lot of people didn't go this time, but a lot of attendees though.
Yeah.
Great
I think I
discovery.
should be able to go to the one in Chicago is the next, right?
Yeah, Chicago.
Yeah, it should be easier.
Yeah, you can
Yeah.
just drive there. That's not too far.
Yeah, exactly. I could probably drive there, right?
Yeah, or take a train.
Yeah. Let's see if more people come up.
Yeah, let's wait for 2 more minutes. Alex says he couldn't join, something comes up, but normally we have a few more people. Let's just give it 2 minutes.
Okay.
Yeah, I think this community meetings really depends on timing. So one of the community meetings, some other ones, I attended. The projected people, lots of people signed up, but because of the timing, only 2 of those showed up.
Yeah, yeah, attendance has been low, but sometimes we got more people, right? It depends. But meeting is recorded anyway. So
Yeah, that's a nice thing. So that's why it's good thing and bad thing. The good thing is you don't have to come here.
At least
The
we got a
bad,
special presentation about Juanmin just for Jing and I.
yeah, we can use the better time. So I prepared more information than necessary just in case.
Okay.
maybe we just wait for 1 more minute, then we get started. Okay. All right, I think already 5 minutes passed. I think we should start. Huami, do you want to you can share your screen, right?
I can share it.
That will be easier.
All right, can you see it?
Yep.
Yeah.
Okay, so we can have good discussion today. Cloud native data center sustainability. So as you know, since I left the SIG storage, there have been a lot of stuff, and most recently on the sustainability. And we created a project called Kepler, and it's just joined the CNCF sandbox a few weeks ago, actually last month. So I just want to share with you all these journeys and visions we got through this time, and hopefully we can have some collaborations to have the sustainable environment for cloud computing. So there are some stats has been going on. So I pulled some of the information from different sources. So the energy efficiency and carbon footprints, if you are looking at different sources, they probably paint different pictures. So I'm trying to be as get the information from unbiased sources, and also can give us some of the benchmarks where we are in terms of the cloud native cloud computing data centers and the overall computing carbon footprint and energy consumption. So by some stats, this is from Nature a few years ago. By some stats, the electricity used by ICT, the infrastructure for computing and transmission, this has been growing very rapidly, and is as high as 10% of the total electricity demand in the globally. And if you're looking at the data centers, this number is about 1%. The other side is that the growth of this electricity used by ICT and data centers is actually faster than many other sectors. And if you compare the carbon footprints of this energy usage, it's comparable to commercial aviation industry, because this is a kind of astonishing. Because if you're looking at the visually, if you are looking at how the aircrafts are taking off and landing, you can see this is a giant equipment. Computers on the other side is really small, but because the amount of the computing devices running in the data centers, the aggregate energy consumption and carbon footprints is quite high. And this is actually before this explosive growth of the large language models. So consider the recent ChatGPT mania. Lots of industry efforts has been devoted to the large language models and AI. So potentially that will generate more computational requirements, and that's will mean the growth of the energy consumption and carbon footprint will be even higher in the future. So the view on my side on the cloud native data center sustainability will come to two fronts. One is the accountability. So how can we measure, monitor, and report the sustainability efforts that is throughout the data centers? That will cover the power consumption, carbon footprint, water usage, and waste management. Some of them are related to each other, but oftentimes we only see the carbon and the power. We do not necessarily see the water and the waste. This is because as the end user or developers, we do not necessarily have the insights in the data center management, but our efforts could make this waste and water and waste even lower. The other one is optimization. So knowing how much environmental impacts our computing environments will generate is not enough. So we have to take actions to optimize our data center environments such that they will consume less resources and will generate the same amount of computations for the end users. This will come to different areas. One is that we're using more efficient energy hardware. So as you can see, many of the CPU vendors pointing that they are more energy efficient than before. So Intel will claim that Intel actually claimed that the new generation of CPU, Sapphire Rapids, is 30% or 20% more energy efficient than before. So if you are looking at Amazon Graviton, over generations, Graviton is more energy efficient than last generation. So these are all good news. The second is that the ambient temperature control and cooling system optimization. This may seem remote to many of us because we do not have controls on the data center, especially the temperature. but that's actually is a false assumption. So if you consider how the heats are generated, so we have the hotspots, and this is not just necessarily the software side hotspot. There are also hardware hotspots. If you have a highly utilized rack in the data center, that's where grow the heat generation exponentially. The heat will not has to be dissipated, and it requires excessive cooling to cool the rack down. That's what generates additional cooling requirements. As many of the data centers are taking actions to lift the temperatures by several degrees. So there's famous publication from Google making the discovery that if you are lifting the temperature by a few degrees, you can save a lot of energy. So the practical usage, that's a practical assumption that the higher the cooling temperature, the more likely you are going to use less electricity. But the downside is that if the hardware components are running in high temperatures, their lifetime will be shortened. And that will generate additional, we'll come back in the next slide, that will generate additional Scope 3 carbon footprint. And thirdly, that's for software architectures, we're using more efficient forms of computations to reduce the footprints of your computation tasks. So in the first generation, we have the virtualizations, and now we have the containers. We also have a lot of computations happens in serverless that can be auto-scaled more efficiently. So these will be additional efforts in architectural designs. Finally, we have these automations and orchestration tools. This will come to the Kubernetes, for example, the auto-scaling, the CI/CD pipelines, and things like that will help us to scale and deploy manifest more efficiently, especially in the sustainability perspective. So the carbon footprints by certain standards, so this is come from the EPA, you can see as a scope 1, 2, 3. The scope 1 is the sources. If you're a data center, the scope 1 will be the sources come from the electricity from the generator. So if you look at how the generators are using the fossil fuels and green energies, renewable energies to generate the electricity, that is the place you want to check. So for certain cloud providers, for example, Google and Amazon and Microsoft Azure, they all have pledges to be 100% green, meaning that they will use green energies for their data centers. So that is very positive. The other thing is that energy is not the only thing. The water consumption is also very significant. So the amount of cooling, the cooling technologies and the heat reductions is still quite significant in the data center environmental sustainability. So what we can do in that front is that we have to be more energy efficient, because green energy itself is usually more expensive than the fossil fuel energy. So the cost side will be up. The more green energy used, the cost side will be even higher. So the more energy efficient will not only reduce the cost, but also give the incentive to use more green energy. The second is that's availability. So green energy, as it defines, are not constantly online all the time. For example, the solar energy and the wind turbine, they only are available when the weather conditions are fine. If they are not, in poor weathers, you may not get this green energy. You are still going to be using fossil energy in that area. So it depends on availability as different regions and time of the day. You may not always get the renewable energy. So you have to choose the locations for computing, so such that the computers will always using green energies. So for the scope 2, that is the power that you use for your actual computation. So this is one of the terms that PUE comes from, the power utilization effectiveness. So in data center, not all the energy are used for computation. So the more efficient the more efficient your data center, the lower the PUE you get. We'll come to that later. So that means quite a few things. So you have to be more efficient on your computation, so to use your energy effectively. The second is that you should also reduce the other side of the energy consumption, including cooling, lighting, and some other things in the data center as well. These somewhat are still related to how software are designed and how systems are deployed. The very last one is come to the scope 3. So how the manufacturing process we are using the energy as well and carbon footprint. So you want to source have a good supply chain, right? That's we are using the less carbon. You can also improve your scope 3 metrics by extending your life of your equipment. So the longer the life of the equipment, the less carbon scope 3 is well introduced. By certain metrics, somebody estimates that some studies estimate that scope 3 could be as high as 80% or 60% or 80% in the public cloud. So that is quite significant. So these are not isolated. So all these scopes 1, 2, 3 are not isolated. They are interrelated. So for example, the scope 3 will be related to scope 2 in certain ways. As I said just before, the higher the data center temperature, the lower the scope 3 impacts. But potentially will be higher for scope 3 because the lifetime of the electronic components will be shortened. So these are some of the trade-offs you have to consider. I just want to put some of the diagrams here to give some of the overviews of what has been progressing over the years. So on the first column, the data center PUE over the years. We started at very high PUE. Over 15 years ago, it was a 2.5. Now, in general, it's a 1.55. In more efficient data centers like Amazon or GCP or public or Microsoft Azure, you can see as low as 1.0 something. These are very quite efficient, but still in aggregate, this is still not. We are still not there yet. And the downside is that the improvement seems to have stagnated over the past 2 years. We have not got a significant improvement in the last 2 years. The other one is that the power consumption by electronic components has been increasing. So I just got this information from the Intel. So for somewhat fair comparison, I just focus on 16 cores and focus on TDP of that year. And I compile that information by using ChatGPT. So it looks to me that over the years, even though the CPU become more and more powerful, the energy consumption also increases quite a lot. We should not also look at these metrics by isolation. The more power it uses, the more computation it can generate. So that's if you are using the power more efficiently by the given computation power, it's still worth something. But that's still the more power, the more heat, and the more cooling. So we have to take everything in a holistic view. The very last one is somewhat related to how we use the energy in our computation architecture design. Is that the efficiency of using power has stagnated over the years. So this is a study by, we'll look at how the benchmarks. One of the benchmarks called spec power is by the standard body. You run this standard spec power test suite on the server as different utilization level, and you get the energy consumption at that level, and you plot out the diagram. You see, over the past few years, the energy efficiency defined by the spec power metrics over the utilization is stagnated as well. This means two things. The more the utilization your server is the more efficient, the more the linearities of the power consumption will maintain. But that linearity will only maintain at certain points, and then it becomes inverted. So meaning that at a certain utilization, somewhat around 70% or 80%, you will use more power to generate additional computation improvements. So that's where compared to the other idea. If you are using a single server and you overloaded the single server, the amount of energy you are using probably is not as good as if you are using the two servers used as half capacity. So that's a potential how we are going to define the vertical and the horizontal scaling in that perspective. Since this is static storage, I also want to place some colors in storage. So traditional thinking is that NVMe is going to replace, SSD is going to replace the hard drive because it's higher density, the high performance. But if you're looking at the energy perspective, the matrix does not say the same thing. So if you're looking at the two Seagate products, the first one, the top one is the SSD. The second one is the hard drive. So by terabytes per year, SSD generates 20 kilos of carbon versus about 2 kilos from hard drive at the same capacity. This actually comes from two sides. One is that because SSD generally does not have the same capacity as HDD. You could easily get 20 gig of HDD, but you are not always to get the same capacity from SSD. Oftentimes you see 4 terabytes and 8 terabytes. That is in the mainstream market product. So by that matrix, HDD is highly packed. So we can see per unit level power consumption from HDD is actually more carbon friendly than SSD. But does this mean that we are going to use by the way, this does not have any performance metrics here. So if you are define the performance metrics like the IOPS per carbon, then the information may be somewhat deviated to a different direction. So that's one of the studies Yuval and I trying to get answers in this KubeCon Europe conference. So the other one is we're looking at the storage architectures. What's the storage policies and data placements and other technologies can reduce the energy consumption and in turn also reduce the carbon footprints. So this the first one from cache policies. This was this study was published 10 years ago, but I think it still makes sense. I have not seen any of the refresh yet. I do not see any of the newer study, but I think these numbers are still making sense. So if you look at the two tables, the top one is the iSCSI. The first column is iSCSI writes. The second one is device mapper cache, which writes through cache policy. The WT means writes through. And then the third column is device mapper, which writes back. And then so is the fourth one. I forgot what the M and H stand for, but I think they are both writes back policies. So for SCSI, if you do not have any of the cache policies, the amount of energy in that workloads in Joule is about 172,000. So with cache write through, you about have about the same. Actually, you have about the same using about the same energy, but you're using a write back, you can achieve a significant reduce the energy consumption for the same purpose. In our best case scenarios, you are using about 60% of the energy as without any cache policies. So this means at certain points, caching is doing a lot of help for certain workloads to reduce energy consumption. So if we also see cache is good thing for scalability, for performance, but that also does not tell what's the impact for sustainability and energy consumption. But given that numbers are some thoughts, this means that you have to put some additional device into the architecture, and that additional device itself will introduce some of the carbon footprints. So you have to look at the overall picture. For the long term, would that cache be helpful to reduce the carbon footprints over life? It's still a question to be asked. It's still we still need some good answers. I have not seen anybody done that studies yet. So hopefully the community in general can help achieve certain insights into that side direction. The second is the study, that is more or less recent from the IEEE transaction on sustainable computing last year. So this simulated results trying to paint the picture that if you place the data in the optimal way, I have to go back to look at the paper. So what's the optimal way is defined. Then balanced rate. Balanced rate just evenly distributed the data across the storage cluster. You will see a difference of energy profiles. And in the best case scenario, so if you have a lot of data, that is as the x-axis, you have lots of data and you place them in the optimal way, you save about 30% to 40%, depends where you are. And that is quite significant as well. Again, this will also means has a lot of implications. So large clusters, if you want to place this in optimal way, you have to also take into account of the computation and networking. So I think this is a good study for simulation, but to answer the question with more evidence, we have to use in a certain validation method to get some real world workloads and get that answers directly. So I have not seen any of the publications on other technologies. I just put them here. So for example, the storage compute co-location, something like HDFS. HDFS did a very excellent job by co-locating the compute and file using MapReduce and the multiple copies. So this will reduce the energy consumption from networks and also accelerate the computation. That also will reduce energy consumption on computing. So this has to also be start looking at from different lens. As I said earlier, the hotspots issue, right? So if you're looking at hotspots in a single rack, that will actually has a lot of implications versus if you are just distribute the workloads evenly across the data center. So not using the higher utilization. So if you are co-locate the storage and the compute, the chances you're going to generate hotspots is higher. Because if you're, I think for certain storage, distributed storages, you have the placement policies to have one copy locally, one copy in the rack, and one copy remotely. So if you apply that placement policies, and then that's rack for lots of copies, they are likely to be the bottleneck, and that bottleneck will generate a lot of heat, and that heat will require additional heating. So that's cascading effects will be causing a lot of different design perspectives. So the computational storage. So if you're looking at how storage and the compute are done separately, so the storage is treated as dumb storage, and compute is handling all these applications like encryption, compression, deduplication, things like that. And nowadays there were additional requirements for neural network processing and for large language models. We do want to do similarity search. These are the computational requirements that potentially can be implemented in storage. How that will be done is still TBD. Whether that will generate less energy, I think there's a good potential. As long as the first principle, just be as close to the data as possible. The second principle, not to generate hotspots. So that will hopefully help the computational storage more efficient than others. And also keep the storage and the storage parts hibernated or reduce their energy consumption or reduce their utilization. Resource consumption will also help to reduce the energy and storage energy consumption. Now auto scaling, which we had a talk a few times ago, based on the utilization, you can auto scale or reuse the Ceph, and you can reduce the the Ceph part by their resource consumptions, and then reduce the computational overhead, and that's in consequence will reduce the energy as well. So that could also be used for further tuning. Now this is time for introducing Kepler. So Kepler, as I said earlier, is a CNCF sandbox project. The goal is Kepler to help us to get insights into the workload energy consumption, and by obtaining these metrics from your computational workload. So these workloads could be at the container level, the process level, and the pod level. With that information, you can design your systems in such a way that will reduce the energy consumption by auto scaling and energy well scheduling. And potentially that's metrics can also help you to realign your overall system deployments to be more energy efficient. So the projects can be found here in the link below. So this is a quick architectural overview of Kepler. So Kepler is based on scientific research that has been done in workload management, energy management for a long time. So what Kepler is different from this research is that it makes all these ideas possible in a software package in a very efficient way. So we use an eBPF to collect the information from hardware and also from software. We get a different C-group metrics. And we're using these metrics and the machine learning models to help you to understand how much energy consumed by the pod. And then we export that information to the Prometheus. And then your workloads and your autoscalers can use that metrics to schedule and report your energy consumptions. So this is a very quick overview. So how Kepler can be used in the your environment, in your system. And so we envision that at least 5 ways the energy power consumption metrics can help you. One is that you really want to aggregate this information to help you understand what's your workload, what's your energy consumption at your workload, tenant, or cluster level. But this will help you to identify who's using energy and what workloads is using energy. And then you can take actions to manually or just automatically tune these workloads and tune these applications. The second of all is that for certain other things, that is not at the pod level, you can provide some of the methods to estimate at a service level how much energy consumed, which is indirect measurements. That is coming to the next section of the next part of this talk. So the third one is that we can use in the metrics to design the schedulers and the scalers to take energy into account when they are scheduled on an auto-scaled workload. So we also have some of the work in that. So KubeCon 2022, so we have provided some of the methods using VPA, Kubernetes VPA, to auto-scale the pod resource profile such that this will reduce the energy consumption in general. The very last one is that if you put Kepler into the CI/CD pipelines and you continuously test your software packages to see how much energy is consumed, this will also help us to develop the green softwares. I see I already used the 30 minutes. Should I go ahead or just should I? The rest of the talk is actually come from the KubeCon Europe. So if you have the access to the recordings, you can watch from there. Maybe you can use this time for discussion if you have any.
I think you can actually continue. I mean, I have some questions, maybe others have too. We can also discuss that later.
Okay.
At the end. I mean, what about others think?
Yeah, that's fine. I have one question, but I'll leave it to the end.
Okay. Always the best to the last. All right. So so I just want to come to the second one, the service level power consumption. So for certain things that cannot be measured directly, can we come up with some methodologies to estimate? So if you are using for example, if you are using Amazon services, they will give you some of the carbon dashboard to help you to understand how much energy used by your EC2 and certain other things. This we call the direct measurements, because you can get some of the metrics from your workloads, get some metrics from your virtual machines, and then you correlate the energy used by your servers to estimate the energy consumption by that entity. But for indirect measurements, for example, if I ask how much energy by S3, then this becomes very tricky because S3 is not a single entity. It consists of multiple services running behind. It consists of the front end, the back end, and the storage. How can we get everything put together so that we can answer the question? This is the amount of energy used by your S3 bucket. So this is the question we want to provide a methodology to. So there's at least the 3 problems we identified. So the one is that because all the distributed storages are handled by computational workloads. So you are using, for example, in Rook, Rook is all the staff containers. You run all staff workloads are running containers. So these are the containers where we consume energy. The second is that how can we trace the S3 request such that we know by what time which path gets involved and to do what kind of work? So this is a question we also want to have. Fortunately, Evo have used the OTel and the Jaeger to provide traces to S3 along the path of the processing. So the RGW and the staff part, so we can trace everything, and we can use the Kepler to measure the part level consumption and attribute the using the trace information to attribute the energy consumption to that S3 process. So the overall picture is looked at this way. So when the S3 requests come in, the RGW and the staff part will process the S3 request, and this request processing will be traced, and the trace will be sent to the Jaeger, and then we correlate with the Kepler power matrix with the Jaeger traces, and then we can we can attribute the energy to that S3 bucket. So this is overall architecture. The rook and ceph level. So this, I think most of the people here already understand how rook and ceph works, so I can just skip it. So when the telemetry and the Jaeger SDKs plugged into RGW and OSDs, this is the picture. So when S3 request landed in RGW, the first intercept, whenever these the IO activities, the start time of the request and end time of the request leaves the RGW part will be recorded. So that's duration will be saved as a Jaeger. And then so the same thing for OSDs. The arrival and exit time will be recorded for the Windows request processing, and that will be also be positioned in the Jaeger collector. And then we are using this duration to, and for example, if you have the OSD pass is running for 10 seconds, and there's two requests coming to OSD. One takes 2 seconds, the other one takes 5 seconds. Then by ratio method, you attribute the first one 10% and 20% of the OSD energy consumption, and attributes 30% of the energy to the second request. So that's roughly how our methodology works. So these are some of the Prometheus level aggregations, charts on Prometheus UIs. So we look at how what's the energy consumption by part, especially in this case, we use on the left side, we look at the namespace level. So as a different namespaces, what's the energy in watts? So certain namespaces use more energy than the others. So if you see the top one, which is gray, is a system. This is Rook namespace. It consumes about close to 120 watts because Rook has a lot of parts running inside. So that's highest energy consumption. And we can also isolate, if you are looking into the Rook namespace itself on the right side of the query, you can see that we can break down the energy consumption as individual parts. So the highest one, which is around 16 watts, that is about the Rook operator. No, that's enough. Sorry, I cannot tell the difference. The color is too pale to me. Let's see, what's the other one? Yeah, some of the parts use more energy than the others. So that's roughly how our things work. So we measure the energy consumption as different parts, and then we also get the trace information about the duration of the process, the S3 processing, and then we evenly distributed the information, like distributed the energy to that duration, and then we get the energy for that bucket. So in this analytics, so we collect on left side, the traces has the different information about which part this S3 request will come into, and how long this request stays in that part, and which user of that request. So by using that information and using the Kepler information about the part, we can have some of the calculations to get the information about how much energy used by the users or by the bucket. So this is basically how we did it for energy consumption estimation as the service level. Yeah, that's all I have, and hopefully we can start more exciting projects and to help our environments become more sustainable.
Hey, thanks, Huamin. So I have a question. I think when you talk about the collected metrics, so those are all from the node side, right? There is no metrics from the controller side, looks like, right?
Yeah, that's right.
Okay.
So the controller, so we do not measure the cube control plane yet. So
Okay.
that's definitely a good question.
Okay. And do you, so there is this cube state matrix project. I think it's maintained by Signal. I don't know if, do you have any integration with that, or because that I think is collecting a lot of stuff already. I'm not sure if it's already used by.
Actually, we are working with them very closely. So
okay.
Damien, I think Damien, if I remember his name correctly, some other engineers over there. So we had some good exchange of ideas, what can be done, and also the technical challenges they face. Then maybe we can also borrow. We have not, have the deep dive into how we can integrate with each other, but definitely for service level estimates, that could be a very good source of information we can use.
Okay. And another thing is I think maybe it's one of the earlier slides, there was a comparison between SSD and HDD. I was just wondering, what is the conclusion coming out of this? Like what should we do, I guess, when I look at this one?
Right. So I think these numbers only paint the picture of the raw information about the hard drive level energy consumption. It did not give us information about performance per carbon. Yeah. So if you like, it does not get us like the throughput is not there, right? If you put the throughput information here, HDD probably is like 3 gig per second, HDD 100 megabytes per second. Then the picture may change.
Maybe. Okay.
Yeah. But I don't think they are 10 times bigger or higher, the throughput. I could be wrong.
Okay.
Yeah. The other one is does not help us here is that, for certain devices, I think HDD, they are more heat sensitive. So if you are putting the higher heats, a higher temperature, HDD may likely to break than SSD. So it did not give us the information about S3 impact. So if you have longer duration of the device, so hypothetically, I'm not sure if that's true or not. Hypothetically, for SSD can run for 5 years, and HDD can only run for 3 years at the same temperature and the same access rate, then the whole picture will change again. So just take these numbers as a grain of salt.
Sure.
Think about what we can, software level and metrics level, performance per carbon, or extending the life of the devices. How can we improve the life cycles of the devices?
Sure, thanks. Yeah, I was also wonder if Tom has some thoughts about this as well. Tom joined late.
Well, yeah, obviously we've studied it a ton, and trying to look at various trade-offs, in just even how fast you spin or how fast you seek on a hard drive versus how many active program array cycles you have going on in an SSD. These are the key kind of things that consume power. And so how do you move that up into decisions that users want to make, and you have to kind of come down from a copy on write file system onto the storage tiering and how snapshots, and it all gets quickly stirred into chili in a little different recipe for every deployment. And then you're spot on how to pick the right metrics. Is it watts per megabyte per second? Is that the right things to optimize? Watts per IOP per second? We know we're going to have 2 tiers or multiple tiers of storage. So do you let each tier kind of compete on its own metric? These are really interesting questions, and how to change the consumption model or the consumption workload so that it's friendly. I think that's the
Right. Yes.
And
Yeah.
and in there is also data movement, because it burns power to move and replicate across the country, or across availability zones. So when does it make sense to do erasure coding within a building, and when does it make sense to do it across sites? So these are interesting questions.
Yeah, completely agree. So I think that once we opened up discussions about carbon and energy, and this, by the way, these are not necessarily tightly coupled concepts. You know, carbon has as scope 3, and energy is just scope 2. So by having these two metrics into the computation architectural design, and there's lots of opportunities. We can do the tunings and with considerations. What needs to be done in the right way, such that the overall environmental impact will be reduced.
The other thing that is tangent or close to this is immersion cooling, and some of the benefits that you get out of that for lower power consumption for the cooling, and higher reliability as you're able to control a tighter temperature range. So it's really worthy study, and it's got a lot of factors involved.
Yeah, when you say immersion cooling, do you mean the ocean data center?
No, we've been looking at how to bathe servers and drives in a Florner or two-phase. I think the latest two-phase products got put on hold because of some safety concerns. But in doing that, that ability to extract the heat out of the data center gets more efficient, which then helps the overall power management and cost.
Yeah, that definitely makes sense. And I think there were some other technologies that's using the heat generated by your data center to warm the office water. So if you go to the office, the data center and the office are co-located, by the way, which I don't necessarily think that's the case in the US. But in many of the data centers in Europe, they are using these co-located environments to warm the waters that are used by the office next door. So potentially that will also reduce the overall energy consumption, because the office next door may not need to warm their waters by using additional electricity. So that's potentially yes, another way to reuse the heat, not to cool the heat.
Yeah, and that's great for teenagers that take long showers, like in my house.
Oh, I have to buy additional server to do that.
Right. Everybody needs a server.
There we go. We have this distributed server data center. Right. That's also a good discussion. Maybe that could happen. Yeah. So maybe IPFS is the solution. All the data distributed and no centralized heating is required.
Everybody gets a server.
Yes.
Right.
I said another question. Just your thought and your guess on this. What is like the comparison between the lifetime of component? Like if you let the temperature go up, as you were saying from Google, but that reduces the lifetime of components, versus when a component needs to be replaced anyway because it's not efficient anymore.
Yeah, I think that is very. I actually gave that quite a thought recently, because again, this is also from Google. So the study from Google data center says by raising the temperatures by several degrees, I forgot how many degrees, I think less than 3 degrees, they are quite reducing the energy consumption by a lot. And there's yet another, this from Google's financial reports. They have the, what is replacement, the server replacement cycles. Every 3 years, you replace the servers. First, they can extended to 4 years. So I don't know what is the, intuitively you have higher temperature, you have the shorter cycles. But if you have longer times of the devices, that's where actually give you a conflicting information. So maybe the cooling technologies improved a lot. So even by increase the temperature in the data center, you're still able to extend the traditional 3 years recycle to 4 years. So that's my guess.
Okay, cool.
Yeah.
Thank you.
Yeah, but anyway, whenever I hear my MacBook just spins the fan, I know something is not happening. It's not going on right. I just shut everything down. Yeah, that's all. Hopefully we can come up with some of the ideas and work together for the storage team as well as for the general sustainability tag to work on some of the projects.
Yeah,
Cool.
Huamin, I wonder, so you, I remember you mentioned you have been also giving presentations in other tags, right?
Yeah.
What are the kind of projects that you guys come up?
We have the, maybe I can quickly show the, so we have the capital projects in the CNCF, but underneath the sustainable computing, we have yes some other projects as well. For auto scaling, we have the Clever project, which is a VPA. So this was given as KubeCon last year. So the idea is that the energy consumption is related to the frequency of the CPU. The higher the frequency, the more likely you will generate more heat. So by reducing the frequency, you will be more energy efficient. But that also means you slow down your workload. So the VPA idea is that if you are not handling quite a lot of activities, we can let you running at a lower frequency, but I will give you more CPU cycles. That is VPA's job. So resize your part. So in general, that's where you reduce your computational requirements. So that's one of the ideas. But this is, by the way, this is not always work because many of the workloads does not want you to change the more memory, more CPU, or less memory, less CPU. This will cause some confusion to the application. That's one of the ideas you can think of over there. The other things we are thinking of, but we have not tried yet, is that, for example, the database, this could also be true to storage as well. The database, this going back to computer 101, you have different sorting algorithms, right? Database is all about data processing. The sorting is sometimes memory intensive, sometimes CPU computation intensive. If you are giving it a lot of CPU, you can move the sorting to CPU. If you have less CPU, you can move the data to the memory, and you can use a different mechanisms for sorting. So, but CPU and memory, they consume power at a different level. You probably can have more CPU cores by if you are sorting if you have the same performance, the combinations of different CPU cores and memory sizes would have different power profiles. Maybe for database tuning, you can take the energy consumption into the tuning, so that you will get the best energy from the combination different CPU and memory resources. So you have the same performance. But we have not got time to make that happen yet. We know how to measure the CPU and the memory consumption, but we do not know, we do not have that time to tune the database to achieve that fine tuning yet. So the same idea probably going back to storage. So if you are running your path, my whole storage concept is based on cluster and stuff. If you have different combinations of CPUs and memory, and for handle the services like we just said erasure code. So the more CPU and more CPU or more memory, these are two options. Which one gives you the highest performance per power option is a TBD. I think there could be a lot of studies and also experimentations can be done in that perspective. That also gives the different tuning opportunities based on different workloads as well. So if that is something we can work together, I think it's very beneficial to the end users to give them best practices for energy available configurations. This is how we do the business, and these are also the tools we use, and what's the expected result. Yeah, that's some of the things we can, this is somehow low-hanging fruits we can think of. And there are definitely more things we can do. More things can be done.
Yeah.
I had just a quick question. Maybe this is out of scope, but have you studied some of these applications in their throughput for power consumption on x86 versus ARM?
We get that request all the time. The problem with that is most of the requirements are actually from the AWS Graviton. Can we compare side-by-side this energy consumption and throughput from the application by x86 and Graviton? But unfortunately, we do not have ideas how to measure the energy from Graviton. So we reduce that, we minimize the scope to ampere. I think that's the word. These ARMS vendors that also have their own CPUs on Amazon as well. So if you compare ampere and x86, which give you a better performance per watt. We have not got to that point yet, because ampere, the kernel modules to measure the ampere CPU's energy consumption and memory consumption are not over there yet. We can measure the CPU, but we cannot measure the memory. Because the kernel module was only arrived end of the last year, and it's not in our mainstream kernel product yet, so we cannot measure it directly. We probably can give you some ideas about CPU, but not on the overall level. But because the ARM CPU and the Intel CPU, they are designed differently, so the memory, if you are missing the memory picture, that's probably not a good indication which one is more efficient than the others.
You don't have any tie-in to the baseboard management or Redfish to try to extract it.
You must be reading my reports all the time. We just stand up the Redfish supports yesterday. Now you're asking the question. You should join us. Yeah, so that's definitely the direction we want to pursue. So at the Redfish level, at the BMC level, if you are getting the information, so which we are working at the moment, so Kepler traditionally supports the CPU, GPU, and the DRAM. Now we are supposed to BMC. So once we get the BMC level measurements, then regardless whether that's 86 or ARM, we can always get the information about the server level configuration and server level energy consumption. So that is something we can do, yes.
Thanks. Hey, I wonder, this repo, sustainable computing, is this repo the whole org? Does this belong to the sustainable tag?
Yeah.
No.
We donate the whole organization to CNCF. So everything here is yeah. So I see.
So it's not okay. So but it's not really like part of the tag sustainability, but it's more like an independent project in CNCF, right?
Yeah. So that is a CNCF project. But actually, I think the CNCF sandboxing, they changed the way. So you see here, we have the environmental sustainability tag here.
Right. So basically, they will be probably evaluating those projects.
Yes. Yeah. So all the collaboration is at the CNCF level. It's a one-free collaboration, and the more you have, the more impact you're going to generate. The impact meaning the both technical as well as environmental. So you are more than welcome to give us suggestions, ideas, and collaboration opportunities, so we can create more good ideas.
Yeah, sounds good. We only have 1 minute left. Yeah, this is a great presentation, great discussions. So but if anyone who are interested in contribute to Kepler or Clever or some of those other projects that Huamin mentioned, maybe we can collaborate with them. Yeah,
that's great. Yeah.
We can definitely talk about this more. I know we are running out of time.
Yeah. And yeah, in the future, if you need me in the tag meeting, just ping me.
Okay. Yeah, sure. We'll do that. Thank you very much.
All right. Thank
Okay.
you. Mhm.
Bye.